All right, so let's analyze the physics of this. So Coulombic or electrostatic attraction depends on 2 or 3 things depending on how you're counting. One is the magnitude of the charges, so +1, -2, stuff like that. And the second are the relative sizes of the ions, and the third is their arrangement in the crystal. Now those are the factors if you are a 3-factor person. If you are a 2-factor person, then these last two can be combined into one, basically telling you about what the distance is between ions in that structure. And you can estimate this by using, the simple, electrostatic physics. And the equation is pretty straightforward. It is this. And so this here is just a constant of nature. But the important part is, again, these are the magnitude of the two charges, and it's divided by the distance. So strong attraction means big charges close together. We know from X-ray studies that the magnesium fluoride distance in MgF2 is about 2 angstroms. Remember, this is about 2 times 10 to the negative 10th meters. And you plug in those numbers and you get an energy of negative 1392 kilojoules per mole. And that is a little lower than we were expecting. Can you figure out what we were not taking into account? Here's a hint. It's roughly half of what we were expecting. All right. So that number basically is what you get for only one magnesium fluoride interaction. And you may recall that the formula for MgF2 is actually that MgF2. So we could double that. And that gives us about almost negative 2800, which makes it a little bit high. So the other thing we need to do is actually take out a little bit for the repulsion that is present between ions of like charge. So when we talk about ionic compounds, we talk a lot about the attractive interactions between ions of opposite charge, rightly so, because that's kind of a big deal, but there is also a large amount of repulsion from ions of the same charge. So in this case, we're looking at the repulsion between magnesium ions and other magnesium ions. And I guess they didn't have any drawn explicitly, but between chloride ions and other chloride ions as well. And you can actually calculate that. This is basically all geometry. You will note that, if you assume this is the magnesium ion in the middle here, the nearest neighbors are all 4 of the nearest neighbors, one that are actually touching with it, are chlorides, opposite charge, lots of attraction. And the next nearest neighbors are other magnesium ions. So that's going to be repulsions, but they're further away, so that might be a little bit less. And there are entire books written about, if you know what the 3-dimensional structure is, and you know what the average distance between the nearest neighbors, between the second nearest neighbors, between the third nearest neighbors, you can actually work out these terms quite precisely and usually calculate and match the experimentally known lattice energies quite well. So let's look at these, shall we? All right, so our current textbook doesn't have a nice big table like this one does, so I borrowed one from another textbook that had a different definition of lattice energies. So for our standpoint, all of these need to have a negative sign in front of them. By Tro's definition, lattice energies are always exothermic. They're always negative. And you can kind of get a feel for how these trends go. So these are all either +1, -1, or +2, -2 pairs. And what makes for a large negative lattice energy, very strong lattice? Well, you want small ions with big charges. So, things like magnesium oxide versus, calcium oxide. So these have big charges. So and these are both +2, -2. But you can see that calcium is a bit larger than magnesium because it's in the next row down and has a smaller lattice energy because of it. The next one down is strontium, and that's even smaller. So it goes from 3850 to 3461 to 32. So that is the effect of size. And let's look at the effect of charge. That most of these, +1, -1 pairs, even small ones like lithium fluoride. So this is +1, -1. These are relatively small elements. They're both in the second row. And this is not even a third the energy of magnesium fluoride. So this is, and if you compare, right, so these are the same row, so they're comparable sizes, but the charge makes a big difference in their lattice energies. So one type of question we can ask you is, given a couple of compounds, which would you expect to have the largest, the most negative lattice energy? And that, I would give you a set where there was only one thing changing at a time, like in this case, the charges are constant, but one of the ions is getting bigger and bigger. Or a series like, LiF and MgO that are comparably sized, but with different charges. So be able to determine that. And remember, by Tro's definition, they're all negative. Now, this reliance on orientation actually explains one of the hallmark properties of ionic compounds, and that's how brittle they are. And so, talked about this a little bit when we talked about different types of solids, but here we go again. So the idea is that, in this real simple two-dimensional world, that the best way to orient or to align particles of opposite charge is to have them alternate. So this is where we got the figure from before, where the nearest neighbors of our magnesium here are all oppositely charged chloride ions. Well, think about the difference between the best possible combination and the worst possible combination. And that is just one atomic diameter. So if everything is shifted down by one slot, then all of a sudden, instead of having opposite charges lined up, similar charges are completely lined up. And this force is quite large, and the whole thing just flies apart. And so this is why, and if you happen to hit it just right, with the right size chisel, sometimes you can get these things to cleave on a nearly atomically flat level on the scale of a couple of inches. But so this is why ionic compounds are brittle and fly apart when you hit them with a hammer. Okay, I guess one last thing. So just to give you another example, here, believe it or not, is enough information for you to determine the lattice energy of rubidium chloride in this case. So here is our figure with ionization energies. We've got here electron affinities. A couple of things about rubidium. So this heat of formation of gaseous rubidium is the same thing as the enthalpy of sublimation. And this enthalpy of formation of chlorine is going to be equivalent to, well, comparable to the bond dissociation energy of Cl2. So hit pause or come back, but scribble these numbers down and you've got all the information you need, and give it a go. And the answer is -691 kilojoules per mole. So let me show you how we got that, if you're interested. All right, and here's how we got that. So usually you start off with the enthalpy of formation, which some of the information said was -430 kilojoules per mole. So the enthalpy of sublimation we actually got from the heat of formation of gas phase rubidium atoms, and that was the +85. So this is the tricky one. I gave you the enthalpy of formation of gaseous chlorine atoms, which was the 121.7 that was in the table. And that is equal to half of the bond dissociation energy of chlorine 2, because you need to dissociate half a mole of chlorine 2 to get 1 mole of chlorine. So that's the 127. And then the next one we had to do was to go from rubidium to rubidium plus. That corresponds to the first ionization energy of rubidium, which is the 403 kilojoules per mole. Then we need to go from chlorine to chloride. So that's the electron affinity of chlorine. And then the last remaining term in this Born-Haber expression is the lattice energy. And if you rearrange and solve all of that for the lattice energy, you get this expression here. Be very careful propagating the sign on the electron affinity terms and the subtraction sign. And that gives you a total of negative 691 kilojoules per mole. All right, one more topic to go, and we'll see you then.